Okay, in the yesterday's class, we are all studied the diesel cycle and then Otto cycle and the mean effective pressures and thermal efficiencies and the various the aspects of derivation. Now let us discuss the one more important derivation. That is the dual cycle. In the dual cycle, as you all know that the same as the various cycles what we are discussed here also it is a same type of cycle, that is the PV diagram and TS diagrams are there in this cycle also, but only the thing is the combination of one fuel with the other, that's why it is called as a dual. For example, in the some of the cars, they are using along with the petrol, they are using gasoline also. Gasoline means LPG gas. See, the both are combinedly they are using as a fuel. That's why it is called as a dual fuel. Okay, that is only the example. But in the real cases, lot of times they are using the dual fuels. Okay, for that also one of the important cycle is the dual fuel cycle. In that PV diagram and TS diagram, let us discuss this different process included in this diagram. 1 to 2 is the isentropic compression. 2 to 3, again, it is what we have studied in the Otto cycle, that is the 2 to 3 is the constant volume heat addition process, and 3 to 4 is the constant pressure heat addition process. Here you must be very careful. Both are perpendicular, these two. While writing the diagram in the examination or else in the test, anywhere, you must be very careful. These two things should be perpendicular to each other, right angle. Okay, Q2 to 3 is the constant pressure, because both will be having same pressure, constant pressure heat addition process, heat addition. Then we will discuss this. Some part of the heat is added in the constant volume, some part of the heat is added in the constant pressure. Q2 to 3 plus Q3 to 4 both are combinedly, they are called as a heat addition process. Okay, both are 2 to 4 is a heat addition takes place. Then you can ask one question, sir, where the cutoff takes place, whether cutoff takes place at 3 or 4. There is a confusion. Here the cutoff takes place at the state end of the state, that is the state 4. That you must be very careful. Okay, 4 to 5 again, it is a somewhat like a expansion process, but it is a reversible adiabatic. It is also called as isentropic. Reversible adiabatic means again the only one equation, that is a T1 by T2 is equal to P1 by P2 raised to the power of gamma minus 1 by gamma is equal to V2 by V1 gamma minus 1. That equation is what's good for both compression as well as expansion. Only the thing is, which one is the higher, which one is the lower, you must be careful. Maybe compression, maybe expansion. Here, the 5 to 1 is the heat rejection process. In this process, you can observe, you see two heat addition process, one heat rejection process, right? Combining both the Otto and dual cycle, diesel cycle, it becomes a dual cycle. You see, the 2 to 3 is the constant volume, constant pressure heat addition. Part of the heat is added in the constant volume, part of the heat is added in the constant pressure, but only one rejection, heat rejection. Let us discuss this temperature versus entropy diagram. T to 1 to 2, it is a S is equal to C, constant entropy. S is nothing but the entropy, constant entropy. It is called as reversible adiabatic. Reversible adiabatic means it can be reversed. The process can be reversed, but there is no heat transfer from the system to surrounding to system. That is called as the reversible adiabatic equation. 2 to 3 is the V is equal to constant. 3 to 4, you observe here. Here V is constant. 2 to 3 is a V constant, but 3 to 4 it is a P is equal to constant, means the pressure is equal to constant. Okay. Okay. 3 to 4 is 3 to 4 is pressure is equal to constant. 4 to 5. 4 to 5 is again entropy is equal to constant. 4 to 5, 5 to 4 to 5 is the entropy is constant, but it is a heat rejection process. 4 to 5, and then this is the 5 to 1. 5 to 1 is the heat rejection at constant volume process. In the words we can see here, in the process, the air is compressed in the cylinder. You can draw the piston and cylinder here. Here it is a cylinder, one, and then piston, bottom dead center is this, and top dead center is this. Piston is movement takes place. In the diesel cycle, I have shown by handwritten. Okay, like that, here also you can write the piston and cylinder. In this process, the air is compressed in the cylinder isentropically from the initial state P1 to P2, P1 to P2, P1, V1, and T1 to P2, V2, T2. Similarly, isochoric or constant volume heat supply. Isochoric or constant volume. This one is 2 to 3 is the constant volume itself. Volume is the same, but pressure is higher. Okay. After the heat supply, heat rejection, all those things you can see here. Directly I'll go to this efficiency, thermal efficiency. Thermal efficiency, as you know that 1 minus heat supply minus heat rejection, or else work done by heat supply. Here heat supply is heat rejection is mCV T5 minus T1. T5 minus T1. Here heat supply is two heat supplies are there. One mCV, T3 minus T2, T3 is and then plus mCP T4 minus T3. That's what T4 minus T3. Here m get cancels. CV if you bring to the denominator it becomes Cp by Cv is gamma, as you all know that. The here ratios are very important. Compression ratio we are assumed or derived in the all the previous derivations. RC is equal to V1 by V2. Cutoff ratio is V4 by V3. This is very important. Cutoff ratio is rho V4 by V3. V4 cutoff takes place here only. And then the expansion ratio is V5 by V4. Expansion ratio is V5 by V4. And from the above relationship, the compression ratio is equal to RE, expansion ratio. This one is E into rho, cutoff ratio. Compression ratio is equal to expansion ratio into cutoff ratio. The one more explosion ratio is there. One is explosion ratio occurs in the 2 to 3. 2 to 3 is constant volume process, P3 by P2. Directly P3 by P2. Here, explosion ratio, cutoff ratio, compression ratio, expansion ratio. Once again, I will tell you where the ratios are coming into picture. 1 to 2 is a compression process. V1 by V2. V1 is higher. Here is the explosion ratio, alpha. Explosion ratio, P3 by P2. Cutoff ratio is a V4 by V3. And expansion ratio, V5 by V4. Right? This is denoted by RC. This is explosion ratio is alpha. Rho is the cutoff ratio. RE is the expansion ratio, right? Now recalling the process 1 to 2 isentropic reversible adiabatic compression, T2 by T1 is equal to V1 by V2 raised to the power of gamma. From there, T2 is equal to T1 RE RC gamma minus 1. From process 2 to 3 isobaric, T3 by T2, P3 by P2. How you can write? Just simply PV is equal to MRT divided by PV is equal to MRT. PV divided by PV is equal to MRT divided by PV is equal to MRT. First, you give the three for numerator and then 2 for denominator. After cancelling all the things, you will get this T3 by T2, T3 by P2 is equal to alpha. T3 is equal to T2 into alpha. T1 alpha is equal to T1 Rs, T2 is equal to T1 RC gamma minus 1 alpha. Process 3 to 4 is again it is a constant pressure heat supply process. T4 by T3, V4 by V3. T4 is equal to T3 into rho. T3 is equal to T1 RC raised to the power of gamma alpha. After substituting all the things, the process 4 to 5 is the T5 by T4, T4 by T5 raised to the power of gamma minus 1, V4 by V1, and then here V5 by V1. Rearranging the things, you will get the rho RC gamma minus 1. T5 is equal to T4 rho RC raised to the power of gamma minus 1. Again, you substitute the T4, what you are found in the previous T4, T3. Again, after that, after finding the T2, you substitute here. After finding T3, you substitute here. After finding T4, you substitute here. You will get the T5. By substituting all the things, you will get the thermal efficiency equations. 1 minus R C gamma minus 1, alpha rho minus 1, alpha minus 1, minus gamma alpha into rho minus 1. This is the equation, thermal efficiency equation for the dual cycle. Mean effective pressure. How to find the mean effective pressure? Here, finding the mean effective pressure, it's a pressure versus volume diagram is further sufficient. These 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 1, as you all know that 1 to 2 is the reversible adiabatic compression, 2 to 3 is the constant volume heat addition, 3 to 4 is the constant pressure heat addition, 4 to 5 is the expansion, reversible adiabatic expansion, 5 to 1 is the rejection, heat rejection. Whatever the cycle, maybe any cycle, the mean effective pressure is pressure applied on the piston while doing the work is called as a mean effective pressure. After burning some fuel, whatever the pressure you are applied on the piston is called as the mean effective pressure. Because here again I'll recall the assumptions what we are assumed. The cycle is reversible, CPCV values are same, and the working fluid is ideal, and the equal quantity of heat is applied. Here, equal quantity of heat is applied to the cycle. Means maybe dual fuel, whatever the quantity of heat is produced, that equal quantity of heat is supplied. After burning, some heat will be liberated. No? The same quantity of heat is applied to the cylinder for the theoretical analysis purpose. Okay. That is the mean effective pressure, as we all know that W net divided by V max minus V minus, V minimum. Q net is V1 minus V2. This is Q supply minus Q rejection. V1 you take out, 1 minus V2 by V1. By substituting all the things, you'll get the mean effective pressure. One more important concept in this, the auto diesel dual cycle. But in the syllabus, you have only the auto and diesel cycle, no dual cycle. So that for the safer side, I am taking all the three for the comparison purpose. The comparison of auto diesel cycle, you can compare the same compression ratio and maximum pressure and temperature. Here, first type of comparison is with the same inlet conditions at the same heat rejection. Depends on the same heat rejection, you can compare. Another one is same same maximum cycle pressure and temperature. You may ask the any one type, but students should be very careful. If we ask the comparison based on the same inlet conditions and same heat rejection, but students are writing this. This is wrong. Whatever the things he is asking, the same particular thing you must write it. Depends on the same maximum cycle pressure and temperature with the same inlet condition. The auto diesel dual cycle, the combustion cycles may be compared based on the same compression ratio, same maximum cycle temperature, keeping the heat rejection constant. For this comparison, you must write it by first auto cycle. You write the auto cycle for the PV diagram, auto cycle, and then you write the two horizontal lines. These two lines, 1, 2. You can give the any convenient numbers, okay? But what type of diagram this is, you must assume. 1, 2, 6, 5 is the auto cycle. Know it. 1, 3, 7, 5 is the diesel cycle. 1, 3, 1, 2, 3, 4, 5, 1 is the dual cycle. Right? Here also same thing. 1, 2, 6, 5, 1 is the auto cycle. 1, 2, 3, 4, 5 is the dual cycle. Same. Whatever the things you are assumed here, 1, 2, 7, 5, 1 is the diesel cycle. But how the efficiency varies? The efficiency is nothing but the depends on this area, efficiency varies. Okay, efficiency varies. Dual and combustion cycles, the diesel dual combustion cycles being plotted on the PV and TS diagram with the same compression ratio. It is observed that area 12651, 12651, 12651 is the whole area, which represents the net work done by the auto cycle on the PV plane. The maximum value of the area is 12751. 12751 is the minimum area, which is represents the work done by the diesel cycle in the minimum. Maximum is auto cycle, this area. Minimum is this area. The similar observation is made with represent the corresponding area on the TS plane, which represents the net heat transfer. Thus, it is conclude that the same compression ratio, fixed inlet conditions, heat rejections, the auto cycle has the maximum efficiency. Maximum efficiency greater than dual cycle, greater than diesel cycle. Okay. Depends on the same maximum, but the condition is the same inlet. Inlet is for all the inlet is same. Outlet heat rejection is same. Heat inlet is same. See, same inlet condition, same heat rejection, same compression ratio. For all diesel cycle 1 to 2, compare the 1 to 2. For the diesel cycle 1, 2, 6, 5, 1, auto cycle compression ratio is same. 1, 2, 7, 5, 1 is the diesel cycle, but 1 to 2 compression ratio is same. 1, 2, 3, 4, 7, 5, 1 is the dual cycle, but compression ratio 1 to 2 is same. For the same compression ratio, same inlet, 2 to 6 is the same inlet conditions, same heat rejection, 5 to 1 is the same inlet. Area of auto cycle is more compared to the diesel, but dual is in between the auto and dual. Auto and diesel. Similarly, we can compare the maximum cycle pressure and temperature with the same inlet conditions and heat rejection. PV and TS planes on which auto, diesel and dual combustion cycles are plotted for the same maximum cycle pressure and temperature. It is observed that 1745 is the dual cycle. First, you must write the dual cycle and then you write the two vertical lines. Okay, two vertical lines. Area, which area is having 12751 is the diesel cycle is having more area. And then 16 4, 5, 1 is the Otto cycle is having the less area, minimum area. 1, 2, 3, 4, 5, 1 is the dual cycle is having intermittent area in between diesel and Otto. That's why the diesel cycle efficiency is more compared to the Otto cycle efficiency, but dual cycle efficiency is in between diesel and Otto. In the TS diagram also, you see the correspondingly PV diagram, you must write it. 1, 1, 7, 4, 5. 1 is the diesel cycle. Otto cycle is 1, 6, 4, 5, 1 is the Otto cycle. Dual cycle is 1, 2, 3, 4, 5, 1 is the dual cycle. But the heat rejection is same here. Heat rejection is same. For maximum temperature is 4. Maximum pressure also 4. For maximum pressure and temperature, the comparison based on the same maximum pressure and temperature and same heat rejection. Okay. You must be very careful. This a lot of times he has asked in the examination. Let us move on to this different problems on the dual cycle. Compression ratio, initial pressure, temperature of an air standard dual cycle is 16 and temperature is 1 minute. Okay. 1 bar. It is 1 bar compression ratio, initial pressure and temperature of a air standard cycle. Dual cycle has 16 and 1 bar and 50 degrees Celsius respectively. The maximum pressure is 70 bar. The equal amount of heat is transferred to air in both the constant volume and the constant pressure process. Determine one is pressure, temperature at the cardinal points of the cycle. Cardinal points means the different states. Cycle, the cycle efficiency and the mean effective pressure of the cycle. Assume CV is 718, CP is 1.005. These two things he has given in the problem, but you must be careful. If not, he is not given. If not, he is given. If not given, you must be assumed this. Another one value, gamma is divide CP value by CV, you get the gamma is equal to 1.4. He has not given. In the problem, if required, you must take it. The dual cycle, the RC is V1 by V2 is 16. V1 by V2 is 16. And P1 is 1 bar. Bar is 10 to the power of 5 Newton per meter square. T3 is 50 plus 273. 273, it becomes 323. And then P3 is 70 bar. 70 into 10 to the power of 5. P3 is maximum pressure. Q3 to 4 is equal to Q2 to 3. Heat supply is nothing but the twice 2 into Q2 to 3. Equal heat supply is there. That's why twice Q3 to 4 is equal to Q2 to 3. It implies that Q supply is 2 into Q2 to 3. twice this. CV value is 0.718 into 10 to the power of 3 joules per kg Kelvin. CP value is 1.005. Gamma value is, as I said, 1.4. You must calculate this. Determine the pressure and temperature at the salient points, cardinal points, whatever you call it as. Salient points, then at different states, and also you may call it as a cardinal points. Thermocycle efficiency, mean effective pressure. Process 1 to 2, it is a reversible adiabatic, P1 by P2 by P1, P1 by V2. As nothing but the RC raised to the power of gamma minus 1, P2 is equal to P1 into. P1 he has given 1 bar 1 into 10 to the power of 5, 16 he has given compression ratio 1.4, it becomes 48.5 into 10 to the power of 5 Newton per meter square. The temperature versus entropy diagram is again dual cycle. I explained this. And state T2 by T1 is equal to V1 by V2 raised to the power of T2 is equal to this. T2 is equal to 7979.15 Kelvin. P1 V1 is equal to V1 is equal to RT1 V1. You will get the V1. In the similarly constant pressure process, constant volume process, P3 by P2, P3 by T2, P2 by T2, T3 by T2. You will get the T3 is equal to 1412.99 Kelvin. Heat supplied is the M2 to Q2 to 3, 2 to 3 is CV, constant volume process, T3 minus T2. You will get the heat supply. Similarly, given that heat supply in 3 to 4 is equal to heat supply in Q2 to 3. Q2 to 3 is MCP T4 minus T3 is nothing but this, and then from here T4 you can calculate. Constant pressure process 3 to 4. Here by substituting all the things you will get the rho. The 4 to 5 like a derivation type, it is a T5. Your calculated T5 is 615 degree Kelvin. Constant volume process 5 to 1, it's again 5 P5 by T5 is P1 by T1. It is P5 is equal to 1.91 into 10 to the power of 5 Newton per meter square. Total heat supply is Q supply 2 into Q2 to 3. 2 into 316, you will get the 623.2 10 to the power of 3 joule per kg. Heat rejection, Q rejection, CV into T5 minus T1. T5 minus T1, you substitute this 210.04 10 to the power of 3 joule per Kelvin. Sufficiency, efficiency, cycle efficiency is 1 minus the Q rejection minus Q supply. 1 minus 210 by 623, you will get the 66.3% of the work done. Work done is Q supply minus Q rejection. You will get this 413.16 into 10 to the power of 3 joule per Kelvin. Stroke is V1 minus V2. V1, take out the V1, 1 minus 1 by RC. You will get the stroke volume is 0.869. Net work done by stroke volume, you will get the mean effective pressure. This completes one problem. Actually, I will complete this session. Okay. Before completing this, once again, I'd like to highlight the importance of this dual cycle. In this session, some of the important things. See, you will give the problem, in the problems, you may twist here. The 1/3 of the heat supply, total heat supply including these two. 1/3 of the heat supply in constant volume, remaining is constant pressure. Okay, the 50% of heat supplied in the constant volume, 50% of heat supplied in the constant pressure. Means total heat supply you will give. Then at the time you divide the total heat supply into 2, you will get the 50%, 50%. Okay. Otherwise, the 0.3% of the heat supply, total heat supply in constant volume, remaining is this. Okay, like that, he is dividing the heat supply in this, the dual problems, dual cycle problems. You must be very, very careful. And then heat rejection. In the comparison, lot of times, the some students, so he is asking the same compression ratio with inlet and temperature, same compression ratio, inlet conditions and outlet, same heat rejection. You must compare this by using this diagram. You must be very, 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 very careful. Otherwise, you will get the 0. The comparison may ask same maximum pressure and temperature. Same maximum pressure and temperature is this. Same maximum and pressure temperature. Same maximum pressure andre, you must write the diesel cycle. Same compression ratio with inlet and exit means you must write the Otto cycle while starting the comparison. Okay, this you must be remember very carefully. Okay,